Problem set 21 is about molecular orbital theory. Molecular orbital theory, similar to valence bond theory that we talked about in problem set 20, molecular orbital theory is also just a theory regarding what a bond is, what it consists of, and why it's formed. Molecular orbital theory is a step beyond valence bond theory in terms of accuracy. You could even say that molecular orbital theory is reality. It's what actually happens. The thing is, because it's reality, it's very complicated, and that's why we still use valence bond theory, because valence bond theory helps us describe a lot of things that molecular orbital theory doesn't necessarily do with much ease. So it's important that we understand both. So we've talked about valence bond theory. Now let's talk about what molecular orbital theory says happens when two atoms bond. So let's use, for example, and I should say the theory behind this is kind of complicated and maybe overwhelming. As a result, what we expect you to do with it is pretty routine and not too overwhelming. So let's talk about some theory. Molecular orbital theory says that two atoms, let's say that we have hydrogen and hydrogen, and they each have one valence orbital. They each have their 1s with one electron in it. They each have their one valence orbital, but we say when they come together to form H2, okay, those two orbitals come together and they kind of squish together and they form two new orbitals, one of which is a lower energy orbital and one is a higher energy orbital. Okay, so let's talk about what this would look like if you had these two s orbitals and they came together. And remember, these orbitals are waves, and so what we say is when they come together, let's see the best way to draw this, and they overlap each other, okay, these two orbitals can add together either constructively or deconstructively. Just like with a wave, if I had a wave like this and I added it to a wave like this, they could add together and they would make a wave that's twice as high. But if I had a wave like this and a wave like this, that's adding together deconstructively, and they would cancel each other out. So this part that overlaps, you can imagine, let's say that that part adds together. What we'd get is we'd get an orbital that looks kind of like a rugby ball. But if those came together and those waves added deconstructively or subtracted from each other, what we'd get is something that looks kind of like a rugby ball with a node down the middle. Now, that's our nuclei. So you can draw our nuclei on all of these. Okay, the nuclei is the same in every single one of these pictures, or every single, well, because we've got hydrogen 1 and hydrogen 2. They come together, okay, and these two add together constructively and make this guy, and deconstructively and make that guy. Okay. Now you can imagine the way these electrons are located between the nuclei. These two are contributing to the bond. These two, with a node in between, are not contributing to the bond. So, without a node between the nuclei, we call that a bonding orbital. With a node between the nuclei, we call that an anti-bonding orbital. Okay. And in this case, where does the electron density lie? Well, it lies between the nuclei. If I drew a line on the nuclei, that's where the electron density is. And so we call this a sigma bonding. And same thing, the electron density lies on that line. We call that sigma antibonding, or sigma star and just sigma. All right, so I come up here. Basically, we take these two 1s's, we squish them together, and when they add constructively, we're going to get a sigma 1s, sigma because it's in line between the nuclei, and 1s because it came from 1s orbitals. We're also going to get a sigma star antibonding 1s. And sometimes you'll see lines that show that the orbitals are coming from other orbitals, but I'm going to draw those better now. There we go. outside, let's draw the two lines. Outside of these two lines, we have atomic orbitals. Inside the two lines, we have molecular orbitals. And we don't have both atomic and molecular, right? We start with atomic, they come together, the atomic orbitals literally go away, and we now have molecular orbitals. Okay, so if we had an H2 molecule, we don't have two orbitals. No longer. We have one orbital like that, the sigma bonding, and then we also have the sigma anti-bonding. Okay, I know it's messy, you're never going to have to draw it, but let's talk about how we fill up this diagram now. Well, we've got two total electrons, so we just fill up from the bottom to the top. Bam. Just like that. All right, so that gives us our sigma 1s and our sigma star 1s. You can imagine that if we had a molecule, actually, we'll talk about that in a minute. Let's see. Nope, we're going to have to talk about it now. So we can imagine if we had a molecule that had, let's say, 2s, 2p, 2s, 2p. Let's say this was O2. Oh, my mistake. Let's say this was O2. So these two s's are going to come and combine just like the 1s's did, and we're going to get a sigma 2s and a sigma star 2s. Okay. Then our two p's are going to come and combine. Let's see what they would make. Well, we have a p like this for each atom. We have a p into the board for each atom, and we have a p horizontal p for each atom. So when these two come and combine, I'm going to get let me draw. Okay, so let's now imagine these parts add together constructively. What you're going to end up getting is something that looks kind of like that, and we usually draw it, sorry, I should have drawn this all lower. We usually just draw it like that. Now, where are our nuclei? Well, they were here and here, so they're here and here, or there and there. And if we get an anti-bonding one where these add up deconstructively, we usually just draw it like, okay, it's just this one with a node down the middle. So where does this overlap happen, or where does this electron density happen? This is happening outside the nucleus. If I were to draw a line, there's no electron density on that line through the nuclei. So because this is outside the nucleus, this is a pi orbital, and this would be pi star. Well, what's going to happen with these one in and out of the board? They're going to be exactly the same, just turned 90 degrees, so this also gives us a pi and a pi star. These ones, when they combine, let's see if I can draw this. If that combines constructively, we're going to get a lower energy like that, and deconstructively get something like that, where our nuclei are right there at the crosses. Whereas this, if I drew a line, that's happening on that line, so we call this a sigma, and this is a sigma star. All right, so when I combine p orbitals, 3 p orbitals from each atom, I'm going to get 2 pi's, 2 pi stars, 1 sigma star. Okay, so if I had like bam, 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 this would be my sigma 2p and my sigma star 2p, my pi 2p, both of those, and pi star 2p. Now the order of these 4 orbitals changes depending on the atom, so I shouldn't even draw oxygen there because I don't know that this is the actual order for oxygen, but you don't need to know the order. You should be able to assign the orbitals, and so if you can just remember, one line is sigma, 2 lines is pi, and star is always above a bonding. So, all right, so there's a brief overview of molecular orbital theory. you can imagine if I had a bunch of electrons in these atomic orbitals on the sides, I could add all those electrons up and just fill up the molecular orbitals in the middle. All right, let's jump over here to the diagram, or sorry, to the actual homework, and let's answer some of these questions. So we want to draw a sigma bonding molecular orbital. Well, we've already drawn that over to the side. This is one example of a sigma bonding molecular orbital. The other one comes from, so that's like a sigma made out of s orbitals. Here's a sigma made out of p orbitals. Sigma antibonding. Well, it's just the sigma with a node down the middle. So, wow, that's really bad. We've got our node and our two nuclei. And this one, node with our nuclei. So this is a sigma with from s's. This is a sigma from p's. Sigma star from s's. Sigma star from p's. Pi bonding. Again, that we just draw like this. That can only come from p's. Pi antibonding looks just like that one up top, but it has a node down the middle saying, nope, don't bond. Say the molecular orbital configuration of a particular molecule is core, and all of that stuff. What's the bond order? Okay, so remember when we did atomic electron configurations, and we would say like 1s2, 2s2, 2p6, 3s2. All this is doing is saying the name of the orbital and the number of electrons in it. The name of the orbital and the number of electrons in it. Well, that's all this is doing. The name of the orbital, number of electrons, name, number of electrons, name, number of electrons. It's just that the names are funky now, but that's okay. Just treat them like names. Let's talk about how to calculate bond order. So we've done bond order with Lewis structures. For example, if I had CO2, I could calculate, or better example, if I had like this, I would say the bond order, because of the resonance, is 4 lines divided by 3 spots. Right? That's how we did bond order with Lewis structures. With molecular orbital theory, bond order equals bonding electrons minus anti-bonding electrons divided by 2. So in this case, how many of these are bonding? Those are bonding because they're not in a star orbital. Those are bonding, those are bonding. That's it. So 2, 4, 8. Anti-bonding, we have, that's anti-bonding, and that's anti-bonding. So minus 5 divided by 2 gives me 3 over 2, which is 1.5. HOMO and LUMO. Okay, HOMO stands for highest occupied molecular orbital. LUMO stands for lowest unoccupied molecular orbital. So highest occupied, I just move up in energy until I get to the last thing with electrons. It's a pi 2p star. So the HOMO is pi 2p star. The LUMO is the lowest unoccupied, last thing with no electrons. So that's going to give me sigma 2p star. Easy enough. Paramagnetic or diamagnetic. This means the same thing as it's meant in the past. Paramagnetic means you have lone electrons somewhere. Diamagnetic means everything is in groups of 2 electrons. Okay, well, in this case, we know there's a 3 right there, which means not all 3 of those could have a pair. So this must be paramagnetic. There must be lone electrons somewhere. All right, let's apply this to actual molecular orbital diagrams. So they give you the diagram. So we just want to fill it in for nitric oxide. How many valence electrons? 5 plus 6 gives us 11. Just need to fill it up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Notice we still follow Hund's rule. Fill up 1, 2, 3, 4 like that. Anytime you're putting electrons into degenerate orbitals. All right, write the molecular orbital electron configuration. So we're going to have our core, as they did on the one before. Followed by, we've got sigma 2s 2. That's not how they wrote it. Put the 2 on the outside. Sigma 2s2, sigma star 2s2. Pi 2p has 4 electrons in it. Sigma 2p has 2 electrons in it. And then pi star 2p has 1 electron in it. You don't have to write an orbital that has no electrons in it. All right, what's the bond order? Okay, bonding minus anti-bonding divided by 2. Bonding, we've got 1, 2, 3, 4, 5, 6, 7, 8. Anti-bonding, we've got 3 divided by 2 gives us 2.5. Homo-LUMO, the HOMO is the pi star 2p, and the LUMO is the sigma star 2p. You'll never have HOMO and LUMO be the same. So even though you have an empty orbital there, okay, that's not the LUMO because the pi star 2p already has one. So they're always going to be different, just like that. Diamagnetic or paramagnetic? Paramagnetic, why? Well, because we have a lone electron. Is the MO description more useful than the valence bond description? More useful is kind of a interesting question. What is it more useful for? Well, it's better for magnetism, right? It's actually better for bond order, and it shows us the energy levels. These orbitals are written in order of energy levels. So the higher is higher energy. Where is it worse? Doesn't show us anything about shape or polarity. But yeah, so I don't know that you could say one's better or one's worse. One's better at something and it is also worse at other things. All right, so now we're going to do this for these two molecules. So CO+, that's 4 plus 6 minus 1, gives me 9 electrons, and this is 5 plus 6 plus 1, gives me 12 electrons. So if this is CO+, and this is NO-, we got 9. 1, 2, 3, 4, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12. Okay, so then predict the bond order for this guy. So for CO+, we're going to have bonding 1, 2, 3, 4, 5, 6, 7, minus 2 divided by 2 gives me 2.5. And NO- is going to be 2, 4, 6, 8, 10, minus 1, 2, 3, 4 over 2 gives me a bond order of 3. Is that right? 1, 2, 3, 4, 5, 6, 7, 8. Sorry. 8 minus 4 divided by 3 gives me a bond order of 2. Magnetic CO+ is going to be para. NO- is also going to be para. They both have lone electrons, which has the weakest bond. All right, so this goes back to our definitions of bond order, right? So higher bond order means higher bond strength, which means lower bond length. So the weakest bond, NO- has the lower bond order, so it's weakest, and CO+ has the higher bond order, so it's shorter. All right, let's keep going. OF+ and NEF+. All right, so this is 6 plus 7 minus 1 gives me 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 8 plus 7 minus 1 gives me 14. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, bond orders. We're going to have OF plus, NEF plus. Bond order bonding is 2, 4, 6, 8 minus 2, 4 over 2 gives me a bond order of 2. NEF plus is 2, 4, 6, 8 bonding minus 2, 4, 6 antibonding divided by 2 gives me a bond order of 1. Magnetic, OF plus is para, NEF plus is diamagnetic. And which is weakest, NEF plus is going to be weaker because it has a lower bond order. What's shorter? OF plus. Okay. This is our last one. Well, that was quick. Number 6, we're now going to do this for O2 minus. O2 minus is 6 plus 6 plus 1 equals 13. And O2 2 minus is 6 plus 6 plus 2, which equals 14. So 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13. And 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14. Okay. Bond order O2 minus is going to be bonding 2, 4, 6, 8. 8 minus antibonding 2, 2, 4, 5. Divided by 2 gives me a bond order of 1.5. O2 2 minus is going to be bonding 2, 4, 6, 8 minus antibonding 2, 4, 6 divided by 2 gives me a bond order of 1. Okay, magnetic properties, O2 minus, O2 2 minus. O2 minus is para with a lone electron. O2 2 minus is dia with everything has partners. Bond length and strengths. So O2 minus bond is going to be shorter and stronger. Okay, so that's pretty much everything we can ask you to do with molecular orbital theory is contained in problems 4, 5, I would say 3, 4, 5, and 6. So hopefully that helps. Again, this is just a different theory of bonding, and it's closer to the truth. There we go.